Somewhere right now, a steel plant is glowing. Inside a blast furnace, iron ore melts at more than 1,500 degrees Celsius. Coke burns. Molten metal pours. And above it all, through chimneys and flues and cooling towers, an invisible river of heat escapes into the sky. It leaves as hot flue gas, as radiant warmth from cooling slabs, as steam that simply vanishes. This is waste heat, and the world produces it on a staggering scale. Studies estimate that industrial processes discard well over half the energy they consume. In steelmaking alone, roughly a third of the energy input is lost as heat that no one captures. Globally, the waste amounts to hundreds of terawatt-hours every year, enough to power entire nations, drifting away for free. Cement kilns do it. Glass furnaces do it. Chemical plants, refineries, aluminium smelters, all of them run hot and vent what they cannot use. For engineers, this represents one of the largest untapped energy resources on the planet. It costs nothing to acquire because it is already being made. The challenge has never been finding the heat. The challenge has always been turning it back into something useful, specifically electricity. And here the story narrows to a single dominant technique. For more than a century, when industry wanted to convert heat into power, it reached for one machine and one idea. You take the waste heat, you use it to boil water, and you drive the resulting steam through a turbine. That turbine spins a generator, and the generator produces current. It is the same fundamental method whether the heat comes from burning coal, splitting atoms, or capturing a steel mill's exhaust. Boil water. Make steam. Spin a shaft. This approach became so universal that few people ever questioned it. It was simply how heat became electricity. But universality can hide a weakness. A method that works everywhere may not work best anywhere in particular. And when the heat source is an industrial furnace rather than a purpose-built power station, the assumptions begin to strain. To understand why, we have to go back to the man who built the first practical version, and to the year everything began. The year is 1884. In Gateshead, England, an engineer named Charles Parsons patents a machine that will define the next century and a half of power generation. His invention is the multi-stage reaction steam turbine. Earlier engineers had tried to make steam spin wheels, but their designs wasted energy in violent, inefficient bursts. Parsons had a subtler idea. Rather than extract all the steam's energy in one blow, he passed it through many rows of blades in sequence, letting it expand gradually, giving up its energy stage by stage. His first turbine produced just 7.5 kilowatts. It was tiny. But it turned at 18,000 revolutions per minute, and it proved a principle that scaled almost without limit. Within decades, Parsons' turbines were driving ships. In 1897, his vessel Turbinia stunned the Royal Navy at a fleet review, outrunning everything afloat at over 34 knots. By the early 20th century, steam turbines were generating electricity for entire cities. The logic was irresistible. Water is cheap, abundant, and safe to handle. When you boil it, it expands enormously. Water becomes steam that occupies over 1,000 times the volume, and that expansion can be harnessed to push turbine blades. Heat water into steam, drive the blades, condense the steam back into water, and repeat. This is the Rankine cycle, and it became the universal language of heat to electricity conversion. Today, the overwhelming majority of the world's electricity is still made this way. Coal plants boil water. Gas plants boil water. Nuclear reactors, for all their sophistication, are essentially very expensive ways to boil water. Solar thermal towers concentrate sunlight to boil water. Whatever the heat source, the final act is almost always steam spinning a turbine descended directly from Parsons. Modern units are giants, producing over 1,000 megawatts from single machines, refined across 140 years of engineering. It is one of the most successful technologies in human history, and yet its dominance rests on the peculiar properties of one substance behaving in one particular way. Those properties are wonderful in a large power station, but they carry hidden costs, costs that become painfully clear the moment you try to shrink the system down. The trouble with steam begins with a number, 100 degrees Celsius, water's boiling point at sea level. To make steam energetic enough to drive an efficient turbine, you must heat it far beyond that, often to 540 degrees or more, and pressurize it to hundreds of atmospheres. This demands enormous heavy equipment, high-pressure boilers, thick steel drums, kilometers of tubing. Then comes the other end of the cycle, and here lies steam's most awkward burden. After the steam passes through the turbine, it must be turned back into water so the cycle can repeat. That requires a condenser, a vast structure that dumps low-grade heat into cooling towers or rivers. Condensers are physically huge because low-pressure steam occupies immense volume. A single power station's condenser can be the size of a building, and the cooling water it consumes runs into millions of liters. All of this is manageable when you are constructing a dedicated power plant on hundreds of hectares. But there is a deeper physical limit. The efficiency of any heat engine depends on the temperature difference between its hot source and its cold sink. Steam turbines were perfected for very high temperatures. When the heat source is cooler, and industrial waste heat is often only 300 to 600 degrees, steam performs poorly. It struggles to extract useful work from moderate temperatures. Water also demands respect for another reason. Below 100 degrees it condenses, and droplets forming inside a turbine erode the blades at supersonic speeds. Engineers must carefully manage where in the machine the steam stays dry. All these constraints, the size, the condensers, the water consumption, the lost efficiency at moderate temperatures, are tolerable when steam has no rival. But for capturing waste heat from a steel mill, they become disqualifying. You cannot build a sprawling boiler and condenser complex beside every furnace. The economics collapse. So engineers began asking a heretical question. What if water was not the ideal working fluid at all? What if some other substance could carry heat through a turbine, without boiling, without condensing, without the bulk? The search led them to a gas that, under the right conditions, stops behaving like a gas at all. The candidate was carbon dioxide, the same gas we exhale and vent from smokestacks. On its own, that seems unremarkable. What matters is how carbon dioxide behaves when you push it past a special threshold, called the critical point. For CO2, that point sits at 31 degrees Celsius and about 74 atmospheres of pressure. Below it, CO2 acts like an ordinary gas or liquid. Above it, something strange happens. The distinction between liquid and gas simply disappears. The substance becomes a supercritical fluid, dense like a liquid, yet free-flowing like a gas. This is the fluid that isn't quite a gas. Supercritical carbon dioxide, or SCO2, is remarkably dense. Near its critical point, it can be several hundred times denser than steam at similar temperatures. And density is everything for a turbine. A denser fluid packs more energy into a smaller volume, which means the machinery that handles it can shrink dramatically. A steam turbine, the height of a house, has an SCO2 equivalent that can fit on a tabletop for the same power output. Now consider how you use it. Instead of the open Rankine cycle where water boils and condenses, SCO2 runs in a closed Brayton-cycle. The fluid never leaves the loop. A compressor squeezes the cool, dense CO2. Waste heat then flows into it through a heat exchanger, raising its temperature and energy. The hot, high-pressure fluid expands through a turbine, spinning the generator. Then it is cooled slightly and returned to the compressor to begin again. No boiling, no condensing into liquid water, no enormous condenser. Crucially, because the fluid stays dense throughout, the compressor consumes remarkably little energy to pressurize it. Near the critical point, CO2 is easy to squeeze. That leaves more of the turbine's output as net electricity. The cycle can also be enhanced with recuperators that recycle internal heat, pushing efficiency higher still. On paper, the advantages are extraordinary, especially for moderate temperature heat. But paper is not steel. A theory becomes real only when someone pours a foundation, welds the pipes, and dares to spin the first machine. In December 2023, in China, someone did exactly that. In December 2023, construction crews broke ground on a project that would test whether supercritical carbon dioxide could leave the laboratory and earn its keep. The name was Chaotan One. Its purpose was deliberately unglamorous. Not to power a city, not to replace a coal station, but to capture waste heat and turn it into electricity using an SCO2 Brayton-cycle turbine. The centerpiece was a single unit rated at 15 megawatts. By the standards of modern steam plants, which routinely exceed 1,000 megawatts, this was modest. But size was never the point. The point was proof. 15 megawatts is large enough to be commercially serious, large enough that failure would be expensive and success would be meaningful, yet small enough to build, test, and learn from quickly. The location mattered as much as the machine. Chaotan One was placed at a steel-adjacent site, positioned to draw on the relentless flow of hot flue gas that steelmaking produces. This was the ideal proving ground for SCO2's central claim. Steel mills generate heat at temperatures where steam turbines perform poorly and where the compactness of SCO2 could shine. If the technology could work anywhere, it should work here, beside the furnaces, capturing energy that would otherwise vanish. Building it was not simple. Supercritical CO2 systems operate at high pressures, and the fluid must be contained within a sealed loop through compressors, turbines, and heat exchangers without leaking. The components were smaller than steam equivalents, but they demanded precision. Seals had to hold. Heat exchangers had to transfer energy efficiently from dirty industrial flue gas into the clean CO2 loop. Every joint was a potential point of failure at pressures that would rupture ordinary plumbing. Throughout 2024 and into 2025, the site took shape. The compact turbine, the recuperators, the piping loops, all assembled around the promise that this arrangement could outperform a far larger steam plant. Engineers were not merely building a power unit. They were staking a claim that 140 years of assumptions could be revised. But a completed structure proves only that something can be built. The harder question waited ahead. Would the compact machine actually deliver the efficiency and the size advantage its physics promised? Stand a supercritical carbon dioxide turbine beside its steam equivalent, and the difference is almost comic. A 15-megawatt SCO2 turbine can fit on a desk. Its blades spin inside a casing no larger than a suitcase, while a steam turbine of the same rating fills a room and demands a hall to house it. The reason lies in density. Near its critical point, carbon dioxide carries roughly 10 times the mass per cubic meter that steam does at comparable conditions. More mass streaming through the blades means more energy extracted per rotation, so the machine can shrink without surrendering output. At Chaotan One, this compactness is not a novelty. It is the entire economic argument. Steel mill flue gases leave sintering lines and coke ovens at temperatures between 300 and 550 degrees Celsius, a band where steam struggles to convert heat efficiently. Below 400 degrees, steam cycles lose ground quickly, wasting a large fraction of the available energy as unrecovered warmth. The closed Brayton-cycle, by contrast, thrives precisely in this mid-temperature window. Engineers estimate that recovering steel flue heat with SCO2 can lift conversion efficiency by 3 to 5 percentage points over an equivalent steam system, a margin that compounds across thousands of operating hours. Then there is the water. A steam plant needs a condenser, cooling towers, treatment chemicals, and a constant supply of clean water, an expensive burden at inland steelworks. The closed carbon dioxide loop recirculates the same charge continuously, sealed against the atmosphere, drawing almost no makeup fluid. Smaller footprint, less water, higher efficiency in the exact temperature range that steel plants produce. On paper, the case writes itself. But paper is not a power grid. A turbine that fits on a desk still has to spin flawlessly for years, absorbing thermal swings as a steel plant ramps and idles, feeding megawatts into a network that tolerates no interruption. The metallurgy, the seals, the heat exchangers, all of it had to prove itself not in a laboratory but under load, on schedule, delivering current. Chaotan One's builders had made their promise in concrete and steel. Now the question was whether the machine would actually turn, and keep turning, when the switch was thrown. In December 2025, roughly 2 years after ground was broken, Chaotan One's first 15-megawatt unit entered commercial operation. The moment carried more weight than a ribbon cutting. Commercial operation means the machine is no longer a demonstration tolerated by patient engineers. It is a supplier bound by the same obligations as any other generator on the grid, expected to deliver contracted power reliably and continuously. The supercritical carbon dioxide turbine spun up, drew heat from the adjacent steel operations waste gases, and pushed electricity onto the network. What the milestone proved was fundamental. A closed Brayton-cycle running on supercritical carbon dioxide could operate at industrial scale, not for hours in a test rig, but around the clock, converting real flue heat into real megawatts. The metallurgy held. The seals contained the high-pressure loop. The compact turbine tolerated the thermal rhythm of a working steel plant. 6 months later, in June 2026, a second unit connected to the grid, doubling the installed capacity and answering a quieter but equally important question, whether the design could be repeated rather than nursed as a one-off. Replication is the threshold every new technology must cross to matter economically. One triumphant prototype changes nothing. A second identical unit, built and commissioned on schedule, signals a manufacturable product. Yet uncertainty remained, and the engineers knew it. 2 units in a handful of operating months are a promising start, not a verdict. The long-term questions still hung open. Would the seals and heat exchangers endure years of pressure cycling without degradation? How would maintenance costs compare to steam over a full decade? Could the supply chain deliver the specialized alloys and precision components at volume and acceptable price? Would efficiency gains survive the messy reality of variable flue temperatures and grid demands? Chaotan One had demonstrated that supercritical carbon dioxide works. It had not yet demonstrated that it works cheaply, durably, and everywhere. And that distinction pointed toward the harder truth waiting beyond the celebration. Because for all its elegance, this technology was never destined to sweep steam aside entirely. The very features that made it brilliant for steel mill flue gases also drew sharp boundaries around where it could compete at all. The temptation, watching Chaotan One succeed, is to imagine supercritical carbon dioxide everywhere, retiring steam across the planet. The engineering says otherwise. SCO2 wins in a specific band, mid-temperature heat between roughly 300 and 600 degrees Celsius, delivered at scales where its compactness and water savings translate into hard cost advantages. Steel mill waste heat sits squarely in that band. So do certain concentrated solar plants, some nuclear designs, and industrial recovery, where cooling water is scarce or expensive. These are the niches where the closed Brayton-cycle genuinely outperforms boiling water. But push beyond that band, and the advantages erode. At the very highest temperatures found in large coal and gas plants, steam's mature technology and enormous installed base remain hard to displace. The economics of a working steam fleet, already built and paid for, resist replacement by any newcomer, however elegant. Then come the engineering constraints. Supercritical carbon dioxide runs at pressures around 200 to 300 bars, far higher than most steam systems, demanding thick-walled components and exotic alloys that cost more per kilogram. Sealing a high-pressure gas is genuinely difficult. Carbon dioxide molecules find leaks that steam would not, and the entire economic case depends on keeping the loop tight for years. The heat exchangers, compact and intricate, must resist fouling and thermal fatigue over long service. And the supply chain for these specialized parts is thin. Nothing like the vast, century-old ecosystem that manufactures steam turbines by the thousand. Cost is the decisive filter. A technology can be more efficient and still lose if its capital expense and maintenance outweigh the fuel it saves. For a steel plant venting free waste heat, the calculation favors SCO2 because the energy input costs nothing and water is dear. For a utility burning fuel at maximum temperature with existing steam infrastructure, the calculation often favors staying put. So this is not a revolution that erases what came before. It is a scalpel, not a bulldozer, cutting into precisely the applications where steam was always weakest and never quite worthy. Understanding that boundary is the key to understanding what Chaotan One actually signals for the world, beyond one Chinese steelworks. So what does Chaotan One truly signal? Not the end of steam, but the arrival of a genuine alternative where none existed before. For 140 years, converting industrial heat to electricity meant boiling water, no matter how poorly water suited the job. Mid-temperature waste heat from steel plants, aluminum smelters, cement kilns, and chemical works has been vented into the sky for over a century, too cool for efficient steam, too valuable to keep losing. Chaotan One proves that a compact, supercritical carbon dioxide turbine can capture a meaningful share of that squandered energy, at industrial scale, on a working timeline, connected to a real grid. The global implications are concrete. The world's steel industry alone vents enough waste heat to power entire cities. Multiply that across every mid-temperature industrial process, and the recoverable energy is measured not in megawatts but in gigawatts, quietly rising as heat that need not be wasted. If SCO2 technology matures, if the seals prove durable, if the supply chain scales and costs fall, waste heat recovery could become standard practice rather than expensive exception. 2 15-megawatt units in China are a beginning, a proof that the physics and the engineering align in the real world. But the verdict must stay measured. This is targeted disruption, not total replacement. Steam will continue to spin in the great power stations, its century of refinement, and its vast installed fleet too entrenched to overturn. Supercritical carbon dioxide will advance where it belongs. In the mid-temperature niches, steam never served well, expanding steadily as confidence in manufacturing catch up to promise. The two technologies will coexist, each claiming the domain it fits best, dividing the landscape of heat by temperature and application rather than by conquest. Chaotan One did not overthrow a 140-year-old order. It drew a new line across it, a boundary defined not by rivalry but by physics itself. On one side, the temperatures and scales where boiling water still reigns. On the other, the mid-temperature waste heat that a denser, smaller, sealed loop can finally reclaim. That is the shape of this narrow revolution, and that is its lasting lesson. Steam ends where carbon dioxide begins.